All right. Thank you, everyone, for joining today. We have an exciting topic focused on some of the latest tools and ideas being used globally in creating Flux networks. Right now, we are witnessing a rapid acceleration in the adoption and scaling of ecosystem flux monitoring tools, similar to what has occurred in the history of weather station adoption. And flux stations now are increasingly becoming very powerful components of networks. And today's talk will outline some of the latest tools and their applications that are pushing the boundaries of flux monitoring globally. My name is Taylor Thomas, and I am the Director of Product Management for LI-COR. I work with hardware and software development for our customers and our partners globally. I have the privilege of introducing our panelist today, Dr. Sasha Ivans. Dr. Ivans is a senior principal scientist at LI-COR. Dr. Ivans received his PhD from Utah State University and has spent his career supporting flux researchers around the world be successful collecting data from eddy covariance systems. He is the chair of the Ag and Forest Meteorology Committee of AMS and the co-chair of the Measurements Committee of AMS. Our presenter today is Dr. George Burba. Dr. Burba is a Science and Strategy Fellow at LI-COR, where he oversees long-term projects and collaborations with external scientific, regulatory, government, and private industry partners. He's also a fellow at the Dougherty Water for Food Institute, is a co-founder of the Carbon Dew Community of Practice, and adjunct faculty at the University of Nebraska. George Burba is an expert in the field of ecosystem flux measurements and eddy covariance in particular, and has pioneered numerous technologies and approaches that are widely used around the world. One quick reminder before we get started, please use the Q&A section of the webinar and ask any questions during the webinar today, and we will address them via the QA feature. And we will also have time at the end for Q&A. And with that, I'll hand things over to Dr. Burba. Thank you.
Thank you very much, Taylor, and thank you very much, Sasha. Let's start with the presentation. So today we're going to talk about latest tools and ideas for establishing dedicated flux networks. And by dedicated, I mean the narrow focus specific task, not general flux network like Ameriflux or LI-COR or even FluxNet, a combination of multiple such network, but much more narrow, topic specific, sometimes commercial flux networks. First, let's spend a couple of minutes describing what we do at LI-COR for those people who are not familiar with our work. So for over 50 years, we innovate by turning complex methods and systems and instruments into sophisticated but simple to use products and solutions. And we focused primarily on natural resource management, agricultural practice optimization, and wide range of various environmental research. And at the bottom, you can see the LI-COR company group, because we expanded a lot in the last few years, and we include all of those companies listed below. So here is the real example, what we've done with the equipment and methodology. So in 1990s and 2000s, the flux measurements with eddy covariance were done using
George,
all, yeah.
sorry to interrupt. Would you mind just making sure that your screen is shared? Looks like it's, want to confirm that everyone can see this. It looks like it's coming through now. Okay, great.
It's just delayed. Is it
Sorry
delayed
to
a little
interrupt
bit?
you.
All right, that's fine. So how long is delay? Like a couple seconds?
I think we're good now. I think we're
Okay.
good now. Thank you.
Yes. So on the left, you can see a multitude of pictures to measure fluxes, GHG fluxes. And those are real pictures. Like, for example, this entire trailer is where we measured methane flux in 1993 to 1996. And this trailer is the photosynthesis measurements and things like this. And in 2010s, we modified everything into this automated station for CO2 and water measurements and methane with net radiation and soil parameters and associated cloud called Flux Suite. And furthermore, now we considerably simplified this configuration. So it's much more automated, it's much more low power, it's lower cost, and we have much more advanced LI-COR Cloud with it. So you can see we went from the left to the center to the right, while the methodology itself is the same. The instrumentation and how that methodology is applied and computed really got streamlined. Now, we were very fortunate to have very significant scientific impact over the years. So this little table shows you the impact factor or something like H index. It's how many papers, original papers, got cited. So if LI-COR instrumentation was the co-author on the paper, then the LI-COR impact would be in this blue digits below. So we would be sitting somewhere between Boston and Brown University, and MIT is at the top of the world. These are world top most cited institutes. So if our instruments were co-authors on the papers where they used, that's where we would sit. So, and we cited every 2 hours, and there is over 73,000 original papers cited our instrumentations. And these papers created very significant impact factor, and they were cited over 2 million times. So for people who are new to this, let's briefly talk about Flux stations. So the Flux stations are very similar to automated weather stations, AWS. You can often see at the airports, on the roof of schools, on mountain passes, on bridges, and so on. But in addition to the weather, Flux station measure greenhouse gas emissions or sequestration, water vapor emission, evapotranspiration, heat flux, either emission or heat flux uptake between surface and the air. And some Flux stations also measure soil radiation and soil parameters to help interpret and gap fill the flux data. So they are, if we start looking at the automated version presented in this picture, they're not that different from weather stations. They just measure, in addition to the temperature, they measure heat flux. In addition to CO2 concentration, they measure CO2 emissions and uptakes, and so on. The methodology deployed by Flux stations in probably more than 90%, maybe even 95% of cases is called eddy covariance, and it works physically in very simple way. So if you have your station located here on the right, and the wind brings 3 molecules of, let's say, CO2 over your field, and this is your field here in the middle, the station measures, and field doesn't add anything to that mean flow. So it's maybe a parking lot. So what station will measure? 3 molecules up, 3 molecules down, 3 molecules up, 3 molecules down. So on the net, your flux will be 0 because this area in the center didn't add anything. And we measure vertical wind speed, and it's a small wobble in the vertical wind speed going up and down, never goes all the way up because we would suffocate, never goes all the way down because we get squished by air column. It just wobbles because of turbulence. But each wobble carries different number of molecules up and down. So now, in the same situation, if we have 3 molecules coming from far away somewhere over the field where we're measuring, and we add 2 more molecules to it, it has to go somewhere because there is a gradient now, and mechanism for that gradient over the land surface is primarily turbulence. So what we'll measure at the station, 5 molecules up, 3 down, 4 up, 2 down. So there will be a bias in the up and down motions. So in a sense, it's like a mass balance over horizontal surface, and it's really very, very direct method. Global coverage is pretty large. And here you can see the map of all existing past and present Flux stations, and they're not a new concept by any means. They're widely used in academia since 1980s. The fundamental physics and math for calculations, not new either. It's developed in 1930s to 1980s, roughly, with some advancement afterwards. What new is the technology to allow flux stations to become accurate, space resolved, nearly fully automated now in 2026, and easily deployed as a networks of multiple low power stations. And this is what we will discuss, because this is the novelty. You don't have to have an institute anymore to deploy a network. You can have a group or a lab or 3 people to deploy a network of 10, 15, or 20 stations. And that changes a lot of different approaches and funding and coverage. So in the final comparison I want to show between weather stations and flux stations is here. You don't have to read all this text. But basically what's happening is if we look at the biggest stages like analog manual deployment and communication or networking of multiple stations, institutionalization and standardization, for example, when it's managed by the region or state or national entity, and level of automation and commercial use, and finally the digital. So this on the left, you see the 5 stages. The flux stations were really behind in 1970s and 1990s compared to weather stations. And they really caught up very quick. So now we just literally, maybe at this point, maybe 3 to 5 years behind the weather station development. Now let's look what led to this catch up and what are the latest few tools. I will discuss only 3 brand new tools here in this presentation. The first one is called Carbon Node. So the Carbon Node is automated flux station. It uses eddy covariance. It's very easy to set up. It's very low power. And for all intents and purposes, it works operationally like automated weather station. But it measures fluxes of CO2, it measures evapotranspiration, it measures heat emission, and incoming photosynthetically active radiation, and all the key supporting weather parameters. And it is designed to help research, commercial, and regulatory sectors to broadly adopt direct flux measurements. So when we make our decisions, we made them on actual measured parameters and not on some kind of derived parameters, or even worse, on the opinions. So our decisions can be objective and more correct. At the heart of Carbon Node is the device called LI-720. This is a simple, cost-effective, cost-optimized sensor for evapotranspiration measurements, CO2, heat flux, PAR, and all the weather parameters. It's very important to note it's different from water node, because Carbon node has 3-dimensional wind speed, it has 10 Hertz sampling rate, and it has the 10 Hertz data stored, but it also does the real-time processing like water node. And in over 32 tests now, we confirm that it's very accurate. It's sometimes similar to the full traditional eddy covariance station, and sometimes it's a little better because it closes energy budget a little better. And I explain it later in Q&A session if somebody wants to know. And this type of device was never available for water or carbon market until now. The simplicity and automation are unprecedented. So we hope this will help transfer the direct flux measurement approach from academic science alone to multitude of practical uses. And hopefully we'll reap many societal and commercial benefits from these direct measurements, starting from very substantial water savings, 20, 30, 40%, to development of the reliable and accurate and fair carbon monitoring, measurement, and verification market. Second tool is LI-COR Cloud. And again, it might look like something what existed before, but it's very, very different in its automation and simplicity. The screenshots in the middle are from the actual LI-COR Cloud. So it's based on our award-winning Internet of Environment approach to allow intelligent networking of many Flux stations. The quality assurance, quality control are automated now. Gap filling is automated now. Footprint analysis, including sophisticated footprint analysis, is automated now. And the high resolution flux mapping also available, which I will discuss and is a separate tool. So now, we're moving from single station to networking on the cloud. And such network operates a lot like Mesonet. Some of you may be familiar with Mesonets. Many states in the United States have Mesonet networks. These are networks of very fancy, advanced, high-quality automated weather stations. And they primarily intended to help economy of that particular state with high precision weather. Now we can use similar approach with the Flux stations. And again, it can be still research, but it also can be commercial and regulatory applications. Here is example of quality control. This is automated now. So here we have a real screenshot from one of our field measurements, and this is footprint for that particular 30 minutes. And this is our long-term flux data. In this case, it's carbon dioxide flux. So you have sequestration negative and emission positive, and they go on daily scale. And here is the example of how data being cleaned. So the original time series had a spike. It was automatically cleaned in this blue time series and gap filled with the green time series. It's all done automated. That's what you see when you open your account and access your stations. Finally, the third new tool I wanted to describe is FluxMapping. So the FluxMapping is collaboration between LI-COR and a company called Atmofacts, which developed high precision ability to map fluxes inside the station footprint, inside what station will see. So on the left is what present station does. So for every 30 minutes, depending on wind direction, it gives you one single blob of flux, which comes from this area. In the middle is what a lot of different techniques people developed based on what we call flux apportioning or footprint apportioning. So these are modeling techniques developed. There is like 6 or 7 of them. So you can have like medium resolution from your footprint. And on the right is the actual flux mapping developed by Atmofacts, which we deploy as a part of LI-COR Cloud. It's an optional feature, and it gives you very high resolution map of your fluxes for every 30 minutes. So you can resolve roughly at the height of your tower. If your tower is 3 meters, your resolution is 3 by 3 meter pixel. And here is the real results. And let me spend a little bit of time with this slide so you can see how novel and in many instances amazing it is. On the left is our flux station. That's our test with University of Nebraska. And here's the footprint of the station over multiple days. And so the flux station coverage, the station's in the middle, there is an access road going on here, then there is a foot trail and the station's here. And this is the same data reanalyzed by FluxMapping. You can now see the actual road. You can now see the wetter and dry parts of the field. And initially we didn't understand what that was, but you can see this is a Levin application. So this is application of an agent which increases sequestration, reduces carbon emission in the soil. So there are 2 plots there, and we can see these plots as well. And so this is created from the math of the eddy covariance itself. And in the first instance, it doesn't even use any maps underneath. It doesn't know topography in the first instance, it doesn't know coverage, and you already have very, very good resolution. You have an option to overlay known maps land use maps and topography maps on it to sharpen the borders. So you can see right now road is a little bit blurred, but you can even sharpen it further, and similar with Olivian applications. But so we came from here to here, and that changes so many things. Agricultural plot testing, the urban environments, any kind of patchy, uneven ecosystems. You can now see and create evapotranspiration or greenhouse gas emission or heat in that type of form where you can address things at very highly resolved scale. So let's look at what these three tools provide as opportunities. First of all, now we have highly resolved fluxes from multiple stations in the network. So we can, of course, connect to remote sensing and scale it from our several fields to the regions, or in some case, we can do the national monitoring, depending on the satellite flyover and satellite products. So the LI-COR Cloud outputs geotagged data, including high-resolution maps after FluxMapping, and now this can be easily scaled up using remote sensing products. Because now each pixel has time and value assigned, and you have the flux for that particular pixel, not just general blob. Here's the actual example. This is example of evapotranspiration done with this type of technique. You can see this is pivot irrigation fields. And so evapotranspiration from satellite is tuned by eddy covariance stations, or you can say eddy covariance stations have been scaled up using remote sensing based evapotranspiration model. So now when we have automatically cleaned and gap filled data for these applications, we can have the entire process almost fully automated in connection with remote sensing. And multiple companies now developing remote sensing based flux models, which are continuously tuned by automated flux station. That's another very important distinction. The model cannot work in perpetuity, correct, because the conditions, underlying conditions will change. So you have to tune it. You can tune it every day, you can tune it every few hours. Again, it depends on the satellite data coming in, because your station data, your station products come in every 30 minutes. So these approaches to fluxes, they work again a lot like automated weather station networks, where the remote sensing based weather models were continuously used to tune to be tuned with ground data. Now, another opportunity, and this one is new. This one never existed in the past. We talked about it for a couple of years, but now it's available and usable. And again, I'll spend a little bit longer on this slide so people can understand it. So when we talk about cross-sharing, we do a lot of cross-sharing on various resources like Uber or Lyft, for example, or Airbnb and stuff like this. So in the commercial world, cross-sharing isn't a new concept, but in scientific world, in many cases it is. So let's look at this. Let's look at this CO2 flux network, and it has all of these stations. And people who are in that network and who run and funded that network, they study CO2. And very often they're not interested in water, or they're not interested in methane. There is another network exists, which focused on evapotranspiration, possibly irrigation. And again, they're not really interested in CO2, and they, in most cases, not interested in methane. And then, of course, there is methane flux network, which exists, where it's typically soil microbiologist and atmospheric physicists studying methane. They typically not interested in CO2 or evapotranspiration. However, they can use the same exact stations in multiple locations, which reduces costs to each of these three networks and effectively adding free stations to 2 out of 3 of these networks. Now with LI-COR Cloud, not only it's possible, it's super easy. It's like creating Gmail account or giving access somebody to Google Doc. It's that simple, and you can start creating these alliances where you can start sharing a lot of the resources. So each shared automated flux station now has much stronger scientific relevance. It's used for 3 different purposes in this example. It can have real-world economic impact, which is 3 times more. And of course, the leverage for grant writing or for any type of funding is very significant because you're asking for less equipment and operation expenses. So you can tell people like, I will give me money for 3 stations, and I will add 3 more. So in total, I'll have 6 because I already agreed with other people. And this way, you can increase the funding opportunities and reduce the operational expense. And of course, it leads to additional collaborations as well in scientific world. And another opportunity which is very new is creating virtual networks. Let's imagine that somebody in Brazil doesn't go to the field, doesn't have money and or expertise, doesn't have enough crew, but they're excellent at modeling and remote sensing. So this person can talk to other network people and ask for access to this station from these people. So these people have these stations. And he says, like, I want mangroves here, and I want mangrove station here, and I want mangrove station there. That person also talks to these people and say, yeah, I want mangroves here and here. So now suddenly this person, and again, it's super easy. It's like giving access to Google Doc. Now that person can have 4 actual stations. That person can form the virtual network of actual station specifically to study mangroves. And that person can unload the workload from people, PIs who give them access to their station. And they can collaborate and they can very, very significantly leverage funding, money, number of publications, and all sorts of outreach potential and so on. So again, with cloud, it's very possible. It's also easy to give certain data. You can give subset of data, not all of your data to that person. If they're only interested in methane and supporting variables, you can give them methane and supporting variables. And this also have never been done before, and the potential is very large with these types of collaboration. And for commercial sector, the same goes. You can give consultants. You can have a consultant in different country and immediately create a network for them of your own stations. So now let's look at actual examples of how you can either save money or save resources or improve science. Let's look at water first. So the water problem is very significant. It's both problem on the merit, because 2 billion people face water scarcity now, and 3 billion more, almost half of the world population by 2050, will have problems with water access. And surprisingly enough, if you only save 5 to 7% of water as evapotranspiration and keep it in the soil, you can solve all the world shortage problem. Like, you can check me. I checked myself several times. I heard it from somebody. I had to recheck it, but it's absolutely true. The evapotranspiration cycle is so huge, just that if we found a way through the cover crops or different canopy, different land management, to save 5 or 10% of this ET and keep it in the soil or groundwater, the shortages of the global water would be solved. However, if we want to go for it, in order for us to effectively manage those areas to save 5 to 10% of water, we have to measure ET over these areas with resolution better than 5 to 10%, because otherwise we wouldn't know if the method worked. If we decided to reduce irrigation or put different type of cover crops on or something like this, and then we see small difference, we need to be able to resolve that difference. It needs to be statistically significant. Such resolution is not practically achievable with models for ET. That includes potential ET, reference ET, maximum ET, equilibrium, PAN, whatever else. It includes anything where you don't measure water molecules traveling up and down. But this type of resolution on daily scale and weekly scale can easily be achieved with automated flux stations. Here is the example for the state of California. The orange line is the state of California prescription for irrigation, and it's all alfalfa. And you have to be on the safe side. Most of these type of prescriptions, they based on potentiality. So it's not how much water got lost, it's how much water could get lost. So it's always tend to be higher. Plus, of course, the state of California have no idea that this farmer in this particular field cut alfalfa here and here and here. So let's look at the combined effect of the difference between directly measured line here and standard prescribed irrigation line. So we saved that farmer almost 40% of water, like 30 to 40% of water. So that's a lot of money, not just in water and resources. It's a fuel or electricity for pivot. It's carbon footprint of this operation in the field. It's cost of the food. So the tail of savings from direct measurements of water suddenly becomes very long and important here. Similar with irrigate alfalfa in Utah, we can see that maximum ET, one of the modeling, typical modeling benchmarks goes here. And again, we're saving very, very significant amount of water as long as we measure direct. Similarly, let's look into carbon and GHG. So there are a lot of debates currently what's better, and mostly the debates are based on the fact that a lot of the carbon issuing agencies got locked in into older protocols and older technology. And it happened a long time ago, and it's very hard for them to get unlocked from this. But automated flux station based MRV, measurement reporting verification, dramatically outperforms traditional currently existing protocols in both temporal and spatial integration. Because we have direct high frequency, high accuracy measurements producing results every 30 minutes with 10 to 20% uncertainty. And the longer you measure, as long as you don't have large gaps, the more you improve that uncertainty. Also, we cover the entire carbon pool, vegetation, soil, water body. If we want to reduce atmospheric CO2 from 440 ppm to 380 ppm, we need to start looking how many ppms we're taking away from the air. That's the measure of effectiveness. And we need to look at it continuously. This is measure of permanency. That's not done with present techniques. I don't have time to go into it, but they're very fragmented and modeled and very limited. So now we can achieve true spatial integration at field scale, and we can capture fluxes over tens of hundreds of acres, and we don't need to extrapolate small plot samples or soil core samples, and we reduce uncertainty across heterogeneous landscapes where multiple sampling is price prohibitive. So this is temporal and spatial integration. Now, in similar way, automated flux station-based MRV dramatically outperforms traditional MRV. The traditional MRV has response time of several years. If you change something today, you'll see the result like 5 years from now. However, if we measure it with flux station, we can immediately see the results of extreme weather, droughts, floods, and so on. We also can immediately see effectiveness of our carbon management. And I'll show you it in the next slides. Like if we apply fertilizer, how much do we increase the carbon sequestration by that fertilizer or biochar and so on. So this way we can very quickly test and create new carbon products and new optimized recipes to increase carbon sequestration in agriculture and forestry in particular, but also carbon reduction in urban environments, so transportation, for example. Finally, it also outperforms traditional MRV in carbon revenue potential. And this one is a tricky one. Because first, we can have apples to apples over wetlands and forests and fields and cities and ocean. It's the same exact method, it's the same exact equipment. Suddenly we're on the plane level field in different environments. Second, we don't need repeat field sampling because we're continuously monitoring. And we don't need manual audits because it's all digital now. You can have automated audits produced. And because we're doing it this way, we have much more accurate MRV at lower cost per ton over time. In the first few months, it's expensive, but it gets cheaper and cheaper and cheaper over time. And as a result, it produces the premium carbon credit. And not because that reduced uncertainty and continuous measurements create what is known as reduced credit discount. So if you can see me, I'll demonstrate it to you. So if you measure your carbon sequestration here with the present methodology and you have error bar around it, large error bar, you're going to get credited at the lower edge of that error bar. So you always will get less money than you should be getting because of that error bar. With the Flux station technique, your error bar will be reduced by a lot. You're still going to get credited for the bottom of the error bar, but it's just be a lot more money. So, so for that reason, it's going to be a more premium product, more accurate product with market prices, stronger verification, and superior confidence in the results. Another thing is everything is automated. Everything's traceable. The data flow, data processing, quality control, it's all the auditable chain. It's digital auditable chain. It's very easy to check. Let's look at real examples here. So on this plot, we have 14 years of continuous carbon sequestration in Harvard Forest. And the up and down oscillations, it's summer uptakes. So this would be summer uptake and winter release, summer uptake, winter release of carbon. So you can see how carbon getting slowly sequestered by this forest, and the forest gaining more and more carbon. You can see which years are better, which years are worse. You monitor that permanence all the time. So such level of tracking is completely out of reach for traditional MRV methods. And of course, if you wish, you can sell the carbon credits generated by this forest to somebody to offset, or perhaps you can inset your own operations. Here's another example. There's a different forest. So this is the birch and spruce forest. And you can see year-to-year variability. So like in 2006 versus 2009, the difference is very large. It's over 2 times in sequestration. But in both cases, you have sequestration. So you can look at the years. It's relatable to insurance products. If you have some type of event like bug infestation, you can immediately have your base and your infested year, and you can claim insurance for this and so on. You can also see if you start some kind of forest management, how you can, if that management improves the sequestration by the forest. Here's a very good example from the ag. So this is from the pasture in Australia. So here before, these 2 adjacent pastures had very similar carbon management. And at this point, the manure fertilizer was added to the green, to one of the 2 pastures. They're next to each other. You can immediately see the results of sequestration. You can see that, oh, manure application really worked well. And it worked well by that much. And by the end of the year, you have almost twice carbon sequestered in the pasture with the manure. So again, nothing like this is possible with present techniques. Similarly, you have 2 different land use types, alfalfa and rice. So for your particular area, you can look which crop is actually sequestering better. If you're interested in agricultural sequestration, for example, like you can see that alfalfa gains carbon much earlier than rice, and it gains probably more carbon than rice because rice loses a lot of carbon here and there. So you can start looking at these things and say like, oh yeah, if I'm getting the same amount of income from two different crops, which one actually lets me sequester more carbon? It will increase my soil. It will make soil more fertile, and I also might be able to sell that carbon. This is wetlands, and this is wetland management example. And you can see here variability in carbon uptake by intermediate restored wetland. So this is before it was restoration started, and this is after restoration started. So that's gained a lot of carbon after it was restored. And again, it can be credited or it can be offsetted, sold for money, or insetted. You can reduce your carbon footprint if you own that land. In urban environment, direct flux measurements, especially with highly resolved footprint, are very novel, very interesting, give you a lot of potential applications, solution, commercial products. I'll show you this one example from our older software, but our newer software can do it better even. So this is our campus at LI-COR, and this is our test plot. It's in the green. And this is our station sitting here in the middle. And we have northern winds in winter, and we have southern winds in summer, and these are our footprints. So when we break these footprints into the green, flux is coming from green areas here, 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 and flux is coming from the non-green areas like roads and parking lots and buildings. We can see that from green areas, we have our normal curve. With sunlight, the CO2 start getting pulled in, and at night we have respiration and CO2 getting produced. Of course, with parking lots, CO2 never gets pulled in, so it's always produced, so it's always higher than zero. But what we see here is three peculiar peaks. And when we overlay this on the traffic density, we can see morning rush hour, evening rush hour, and here we can see lunch. So when you start looking at this advanced use of flux stations combined with the advanced footprint tools, you can start teasing out these things. You also see it from the base. You can see how much carbon was added here and here and here. So city can switch from to electric buses, for example, and immediately see the effects of it. And of course, oil and gas, it's in a sense, it's actually easier application because million parts per million are leaking out of the storage facilities or pipes. So you can easily see and quantify this. This is our paper with Saudi Aramco, where we have used eddy covariance automated flux stations to determine the leakage, artificially created leakage from carbon sequestration storage facility, like modeled, but the actual station, actual measurements, but we created artificial leak, and we can immediately see and quantify that leak. But again, that's probably the easiest case out of all I've described. I also want to take this opportunity to talk about future developments. So a lot of what I've described, or everything I've described, is now possible, automated, and easy. Now, something else which coming in the future, where we can play like as a science community and as a commercial environmental community, we can play a very significant role, is something called ecosystem services. So here is the general concept of ecosystem services. It's been developed for last probably 15 years very actively. You have provisioning services. It's basically our food and drinking water and so on. You have cultural services, recreation, science and education, hunting, fishing, things like this. And you have regulating services, from coastal protection to the bee pollination and so on. So if we start looking at our environment and our use of resources through this lens, we can price each of these services. So the pricing of these services can be modeled. Then it's of course unreliable, subjective or fraudulent or just like misguided. Or we can start looking at a lot of these things through measurements. Like Flux stations not going to play a role in some of these services, but they will play a very significant role in many of these services. Probably quarter of these services can be verified and better modeled or even directly measured with Flux stations. And the potential of this type of scientific research / commercial market is very, very large. You don't have to read, you can read it on your own, but this is something I've pulled from the various assessments, and you can see we're talking about trillions. And this is a couple examples of very nice assignment of dollar values to ecosystem services in very specific locations. On the left is UK, on the right is US, and you can look at it on your own again, so we don't spend time on this. But like, just look at this example where it tells you, oh, this annual outdoor recreation revenue is $8.2 million. So this is what our park brings us. This is what we save in healthcare costs because our people have access to these large lakes and they do a lot of sports activity on the lakes and so on. And the moment we start incorporating in CO2 and water use and heat in this regulatory part of environmental of ecosystem services, we can use Flux stations to inform this type of assessments. And this type of assessments eventually will lead to much, much better decisions on how we use our land and our resources. So I just encourage you to also think about this future application. So final opportunity I'm going to talk about is a few ideas on how you can leverage these new tools and new networks for funding. So like dedicated network typically build around clear economic or ecological objective. So it can monitor a collection of individual farm, or it can monitor a region or entire country for very specific monitoring. It could be water, it could be carbon assessment, national assessment of carbon, and so on. So with narrow core mission, it also collects many additional variables. So in this non-core data, through this cross-sharing or virtual sharing, can now be easily shared with other networks and other entities. Could be commercial, could be university, could be regulatory, doesn't matter because it's now very easy to share. And the focus area and competitive edge of your own research, they stay intact. So if you study methane, you don't share methane. If you don't want to share methane, so you have this dibs on first publication, but you can share the rest. And through this approach, you can add major efficiency to your project and a lot of cost benefits. So that could lead, and I propose people start doing this, to industry alliance. For example, cattle association can work together with soybean board, or hydrology firm can work together with irrigation company. They have different goals, but these goals slightly overlap. And if they have stations, they can share some of these stations or some parameters from some of the stations. If they're not in direct competition to each other, they can really optimize their resources this way. Similar with regional alliances. For example, state weather network like Mesonet can be combined with national. They can collaborate and create alliance with national ecological network or with the state evapotranspiration network, again, saving on the number of stations, on the cost of stations, and each of the participants gets what they want. At the same time, they all save money. Also, we can look at national alliances, like neighborhood countries sharing data for stronger MRV and scaling, and custom collaborations. When you can write to your grant agency, if you give me X amount of money, I will find collaborators which will give me additional stations for the Y amount of money. So you as a funding agency is getting X plus Y return on your investment. And such networks already being operational, and I'll show you 3 examples. So this is dedicated Flux network called Peril 41. It's by Water for Food Global Institute. Currently, it has 19 Flux stations, and it's going to expand. It's specifically dedicated to irrigation and water management. With first station was active in 2018, and now you can see here on the map is because some of the stations located nearby. It's 3 stations in this location, 3 in that, 2 in this. So they're spreading around. Very recent expansion was in Colorado, Upper Colorado River Basin. And the goal of this network is to create highly resolved evapotranspiration maps so farmers know how much they need to irrigate. Effectively, if you know that you lost 2 inches of evapotranspiration in the last few days, you never need to apply more than 2 inches. You already will over-apply a little bit because rain will come. But if you simply replace what you lost, you will save about 30, 40, sometimes percent of water, fuel and energy expenses, and carbon footprint. And while this network is focused on water, it's also start looking into CO2 as a part of water use efficiency. And it also, because of the infrastructure and agricultural connection, start looking at methane and N2O as well. Another good example of dedicated network is Chagas. So this is Irish GHG research network for national scale carbon monitoring. So they have over 30 stations in key agricultural systems and peatlands. And the focus of this network is to improve modeling and mapping and verification of carbon sequestration across all the different land uses of Ireland. It supports multiple carbon assessment approaches, from continuous flux measurements to soil carbon stock, and it's intended to improve management practices for better mitigation and policy development. So the country is looking in its carbon management, basically, and GHG management altogether, and develops the most optimal scenarios which fit economy well, but also it fit ecology well. And another example is upcoming network in the Northern Africa and Arabic Peninsula, possibly developed in further into the Central Asia as well. It's Low Emissions Agriculture Innovation Facility. It evaluates low emission agricultural practices and trying to develop enhanced carbon credits while producing the food. So it uses the direct measurements with flux stations to certify carbon credits and scale with remote sensing. And currently, particular promising approaches are based on the remote sensing models based on AI and machine learning. The idea is to help smallholder farmers generate and sell carbon credits, diversify their income, and reduce their year-to-year risks. So of course, it also will lead to reduced land degradation and improved biodiversity, because the idea is to start taking CO2 out of the air and effectively fertilizing soil with that carbon. And they also now looking to attract corporate carbon market investments. Here's the other efforts. Some of them have dedicated networks, some have single flux stations, some of them uses other people's flux stations, but these are all various commercial companies already using the direct flux measurements for their commercial goals. So in conclusions, I want to state that automated flux networks are ready for dedicated use. They easy to use, they low power, they cost optimized, they not completely cheap, but for the quality they provide, they quite cheap. So they provide a very high quality product, carbon product, water product, GHG product for considerably reduced price in comparison with traditional stations. To get to this, we had to resolve these 6 obstacles which we systematically were resolving. One is understanding of the method, so people are not scared. So it doesn't look like a black box and some kind of magic. So the method makes complete sense, calculation makes sense, reliability makes sense, and so on. We also reduced cost effectiveness because now we have this combined low cost, low power combined sensors. We also automated the calculation process as well as quality control process and gap fill process. We also made tools which make it very easy to cross-share and leverage it, as well as scale with remote sensing. So now everything is ready for dedicated applications. Thank you very much, and we're ready to take your questions.
Excellent. Thank you very much, George, for the excellent presentation. We've had a lot of questions in the Q&A. Please go ahead and ask any additional questions in the Q&A section now. I will ask a few of them live so that we can address them together. And then this recording will be available for attendees afterwards, and we invite you to share that recording with your colleagues as well if they weren't able to join in real time. So one question that came up from multiple users was, uh, can you describe when I should choose a quote unquote traditional eddy covariance system using smart flux and a gas analyzer and an anemometer versus the next generation eddy covariance system in the form of the water node or the carbon node? Maybe a question for Sasha. What could you maybe describe some of the trade-offs or other considerations?
Sure, Taylor. Thank you. Yeah, so that's a great question, and we get those all the time. I would answer it shortly. Use the full eddy covariance system if you are doing really delicate research, because there is a little bit of difference in performance of the sensors, and you will for sure get much more accurate results using the full eddy covariance system. If your application is not heavily research based, any of our cheaper solutions are excellent choice.
Great. Thank you, Sasha. Another question for George. You talked about the concept of virtual networks and shared networks, and you talked about data sharing. This question is about when data comes into LI-COR Cloud, can it be accessible and shared to other web applications as well, or to other data repositories outside of LI-COR Cloud? Can you just describe that a little bit?
Well, I believe it can, but you probably know better. I think you can do API to the other clouds, right?
Yeah, that's right. So yeah, we can do the sharing within LI-COR Cloud via virtual networks, and as you outlined, we've seen many valuable use cases emerge with that. But then, if the ultimate location for the data is with a repository or another web application, the data is available via API. It can also be queried via uh, file sharing approaches as well, kind of more simplistic forms of API. So there are a lot of options for file sharing, but the virtual networks capability is something that we've been really excited about. We are getting close on time, but we have so many questions. Some of these we will have to address afterward, and we'll send the responses to you. But one more question. We've had a few of these around data auditability. How can I ensure that my data is auditable and able to be used for carbon credits or monetization in that way? Maybe a question for you, George.
Yes. So everything in the chain of the data collection, processing, cleaning, gap filling, integration, is now stored. It's like you you can literally repeat. You can take 10 hertz data, you can take 10 times per second data. You can apply, if auditor, let's say, the auditor can apply their own code and get the same result. And if result is different, the auditor can go back and see where the auditor's code is different from our code and what stage it diverged. But from what we know, our code is the best because it's our engine is used by most of the flux calculations in the world, and so the traceability and ability to audit on purpose built in already. We did it like with Taylor and with others. We discussed it many times. We said like as soon as people start paying money for carbon or money for water, we need that ability to audit the data. Yes, so the entire chain is auditable.
Great. Thank you, George, and thank you, Sasha, for answering these questions in real time. Um, we are past our time together. Again, this recording will be shared, and we again appreciate you taking the time out of your schedules. And please reach out to George, Sasha, or myself at any time via email, and we'd be happy to discuss your work, your application, data processing, or setting up dedicated networks. And yeah, we look forward to working together with you and the rest of the community. So have a great day. Thank you.